In this video, I wanted to take a moment to sort of sum up what we've done. And so what we did is we wanted to find a solution which to a differential equation, and a solution to a differential equation is a function. And so we wanted to find a solution to a differential equation that was a function of the three-dimensional polar coordinates. And what we did is we ended up doing a separation of variables. And so we had the radial part of the equation here. And then we had the part that was based on the angles, the angular part. And I went through how to actually solve that in previous videos, but what we end up with are the spherical harmonics here. And so now we have these two equations here that are the separation of variables from our wave equation here. Remember, this is a function, which is why it's called a wave function. This is a function, and the solutions to it are going to be waves, and so hence wave function. And so what we can do then is look at these two different things, so the radial and the angular part of this equation. And so with the angular part, as I said, we got the spherical harmonics, and they look like this. And we know that the spherical harmonics was based on the L and the M. So these variables, and those showed up in the equations that we had, the what are called the Legendre equations, or associated Legendre equations. And so just to kind of quick look at this, what we can see is when L equals 0, so when L equals 0, M has to equal 0. We get this this sort of solid ball. And I put an S here because that is the S orbital. Then when we have L equals 1, then M can be -1, 0, or 1. And so we end up with three different possible waves here, or spherical harmonics, and that is the p orbital. Then when L equals 2, we can have M be -2, -1, 0, 1, or 2, and so we end up with 5 of them. But sort of the thing to notice here, what's going on, is when we have L equals 0, then it's just one, it's essentially just one bump like this. So if this is our probability distribution here, this would be kind of like the s orbital, where the p orbital would be more like this. And you can see, if you kind of turn this into the surface of this ball here, then up here in the red is kind of like where we are here, where it's in the positive, and then in the blue here is where we are here in the negative. And so here where it's green, it's 0. That's where we are crossing the line. And that's why if we look at this table over here, this ends up looking dumbbell shaped, because if we say that green is sort of the positive part and red is the negative part, when we're in between them, that goes that is reduced down to 0, and so we end up getting that node. And similarly, when we have L equals 2, now we have this sort of higher frequency pattern here, where we have the positive in red here, then the negative in blue, and then it repeats faster here, positive in red, negative in blue. And so that's why we end up getting a shape that looks like this, because we have the alternating between green, red, going around like that. And so we can see, like on this one here, where it is green in the middle, right there, it's 0, and that's why we end up, if you're looking down from the top of it here, that there is no density right there. And so we can keep doing that with I mean, as we go up, we're essentially increasing the spatial frequency of these spherical harmonics, where you can see here the frequency is very low. If we go back to this image here, it has just this one long wavelength where when we go to the next one up, we have this wavelength here, or I mean, it's essentially like one full wavelength, where this one's like a half wavelength. And you know, if you keep going, then you'll keep getting higher and higher frequencies. And so that is what the spherical harmonics part is telling us. And the radial part is telling us how this is behaving as we go away from the nucleus. So if 0 here at the origin is our nucleus, and then this is R, which is the same R as this right here, then this part of the equation tells us what's going on as we go away from the nucleus. And so each spherical harmonic would be, and so this is kind of a one-dimensional representation of it, but at this distance, that's not a very straight line, it should be straight up. At this distance, so we'll call that R1, there is some spherical harmonic. And so maybe that would be something that looks like this. But we also have at R1, so maybe we have something that looks like this. And so what we can see is that so this looks like this is like going further off from R1, but essentially what this is there, we can maybe even say that this has different values at different parts of this. So maybe we could even just draw it thicker here, where this has that value right there, because it's not actually extending off into further away from the nucleus. And then maybe we could even well, actually, how about I just use the colors that they have on these spheres here. So this part is red, so that's positive right there. And then we can take blue, and that is where it's negative right there. And then the radial part, as I said, we might have something that looks like this. And this tells us that we take whatever the value is right there for our spherical harmonic and multiply it by the value right there on the radial equation. That's why we have the multiplication right here. And that tells us what the value of the wave function is at that particular point. So, and then you could keep going down the line. So, I mean, you could put these arbitrarily close, but we'll just say R2 is right there. Maybe that has, you know, this spherical harmonic that looks, you know, something similar, something like this. And then we take that spherical harmonic and multiply it by the value of the radial equation at R2. And that's how we end up getting the value of the wave function. And the value of the wave function is, well, it's a probability amplitude, we call it. But if we square it, so if we take our wave function and square it, that gives us the probability of finding the particle there. Because, you know, we're saying that this is negative. There is no physical interpretation of a negative probability, so that's why we use this Born rule and we square it, and that gives us the actual probability. And so that is what this solution is doing, is telling us, so this part here, the radial part, is giving us sort of a distance away from the nucleus, and that would, you could say, would be in all directions. We're not talking about a direction yet. So then this spherical harmonic gives us sort of a direction based on these two angles. And so that will tell us the value of the probability amplitude at, a certain point if we take some specific r, some specific theta, and some specific phi. I mean, if you know about probability, if you zoom in on a single infinitesimal point, the probability drops to zero, but I'm not going to get into that. So say we're just looking at kind of a tiny space around some point at a certain particular r, theta, and phi, we would know the probability in that portion of space. And so I actually have here, so these are the radial equations, which, as I said, are the Legendre equations. And so we can, so as I said, these are radial, so we can say that the origin 0 here is the nucleus, and then the x-axis is how far away from the nucleus we are. And so right now this is the R10, so L equals, or N equals 1 and L equals 0. So we see we have this right here. It's just kind of this in one dimension, that looks like just this single decaying exponential. But if you sort of turn this into a three-dimensional shape, that's how we would end up getting this sphere. Because if we think about it, if this in terms of blowing this up to 3 dimensions, then no matter which direction we go from the nucleus, we would see this same drop off right here in any direction, and so that would look like a sphere in 3 dimensions. Then we can look at n equals 2, L equals 0, and so this gives us this, and like I said, we have density right here, then it goes to 0, but then we have more density right here. So that gives us the 2s orbital, which we don't have pictured here, but it would be kind of a sphere where one of the layers of it was taken out where this reaches 0. But then we can look at the n equals 2 and L equals 1, and we see we have this lobed structure here, and that is sort of these lobes right here. So that's how those look right there, where you can see that at the origin it's at 0, and it goes up, and then it will kind of go down. These are, sort of idealized drawings, so you don't actually see that sort of gradual decay, but you can imagine that this is kind of like that sphere on it. And so then we can look at the 3s orbital, and once again it'll look like a sphere, but it'll have now right here and right here is where it will go to 0. And so it's like we have these two layers within our sphere that are taken out. And we can look at the 3p orbital, and so we have this lobe right here. It goes down, we have a node, and then another lobe right here. And yeah, I don't think this shows that, but if you've ever seen like the images of p orbitals, like you have probably seen. So this would be like the 2p orbital, then the 3p orbital is something that's kind of like this, and then it has this sort of weird thing on both ends like this. And so we have the 0 density right there, which is where this is crossing the x-axis right there. And then we can look at this one, and this is the 3d orbitals. And so the d orbitals are these ones right here. And so you can see, well, I mean, this is showing it with the radial and the angular part of the equation. In this, we're just looking at the radial part of it. But you can see how we end up getting this kind of lobe, but it's at 0 when we are at the nucleus, and that's what we see right here. And so, yeah, these are the radial equations here. And so one other thing I wanted to show, well, there's several more things I still want to show, but one of them is this, and I actually got this from my physical chemistry textbook, and that is the physical chemistry textbook by David W. Ball. And I have the second edition here, but the associated Legendre polynomials. And so the associated Legendre polynomials, remember, are the ones that give us the they're the ones that give us the spherical harmonics. And so what we have here, so this top equation up here, this is the associated Legendre polynomial. We see this over here, that is the Legendre polynomial, which is this right here. But the thing I wanted to point out was that in these polynomials, we end up with this cosine and sine, and then cosine squared, cosine sine. And I thought it was kind of interesting that the order of the cosine and sine are based on the L and M. So the order of cosine is L minus M. And so we see here L is 1 and M is 0. So we have cosine to the first power, but then sine has an order based on M, which is 0, so there is no sine. And I guess we could say that this is, minus the absolute value of M. I should probably say, because we have here 1 and then minus the absolute value of plus or minus 1. Means we don't have any cosines, but we have a sine here now. And you can see how this keeps going. L equals 2. We have the cosine that's that's a second order 2, and then 2 minus 1. So cosine is first order, and then sine is first order. Then L equals 2 minus 2. We have no cosines. We have sine of second order. We can keep going down. So 3, we have cosine of third order. So the highest exponent on a cosine is 3. So that's cosine that is third order. And anyway, like I said, these associated Legendre polynomials are the spherical harmonics. They are part of the spherical harmonic. And so, this I thought was just kind of a nifty way of, thinking about the cosines and sines in the associated Legendre polynomials being dependent on this L and M. And so now the last thing I wanted to show was this. So this is the periodic table, and so this actually shows the spin. So we have the plus and minus spin for each part of it. And I haven't really talked about spin yet in terms of these orbitals, but essentially all it's doing is taking the number of orbitals that we can get from our Schrodinger equation as we have been solving it and doubles it, because we can have the plus half and minus half spin. But this is just showing that when we are in this very left part of the periodic table, we are at L equals 0, and so therefore M must equal 0. And this blue part here is the actinides and lanthanides that I kind of inserted back into the periodic table. So usually you would see it with this blue part sort of taken out and put off to the side, and then this yellow part would kind of be brought back over, because these are the transition metals right here. These are your things like, manganese and iron and cobalt, nickel, copper, that kind of stuff. But we see here, like I said, we have the L equals 0, M equals 0. And then over here we have L equals 1, and therefore M can go between -1 and +1. And we see that this happens twice because we have the two spins. Then we have L equals 2, and so M can range between -2 and +2. And then we have L equals 3, and that can then M can range between -3 and +3. And we see that these quantum numbers that fall out of the equations that we've been working with, these are actually, this is kind of how the periodic table is actually built. And so essentially each one of these different colors here is increasing the L by another 1. And so that's putting in more electrons. So I actually wrote over here, so this is the number of electrons. So at n equals 1, we can have 2 electrons, and that comes from the fact that, there is the spin. And then we have, at n equals 2, we have +8 to our 2, so that gives us 10 electrons that we could possibly have. And I mean, these maximum number of electrons are going to come all the way at the right here, because we fill the orbitals with electrons as we go from left to right. That's sort of a periodic trend, because as we go left to right, we add another proton, and therefore we add another electron in order to make it a neutral element. But anyway, so the main takeaway from this is that I wanted to show that these quantum numbers determine how the periodic table is built, and sort of the structure that the periodic table has taken is based on all the stuff that we've been talking about. And that's sort of the connection here with the quantum mechanics and chemistry, which in future videos I'm going to start making that more explicit as I actually sort of veer my way into more chemistry related things. But there is still a bit more of the quantum mechanics to get through, including the angular momentum and spin, and then looking at multi atom objects. So essentially solving the Schrodinger equation for H2 for 2 hydrogens bound together, and things like that, before we get into the chemistry of it, at which point I'll start talking about the things like shielding and stuff like that, and getting into sort of why, when we are at n equals 3 here, do we not have any of these d orbitals? So why do we not start filling the d orbitals until we get to n equals 4, when n equals 3 is where L can be equal to 2? And so there are reasons that have to do with atomic orbitals and shielding, and sort of, which is the way that like electrons in lower shells sort of block that charge from electrons in higher shells. But anyway, I'm getting ahead of myself. This, like I said, there is still a bit more quantum mechanics to get through, and I hope you found this video helpful as a way to sort of bring together the stuff that I've talked about in like the infinite spherical potential and in the hydrogen atom solutions to the Schrodinger equation. But anyway, I hope you found this video useful, and I will see you in another video.